Okay, it's my really great pleasure to introduce next speaker, Bill Thurston. I was told that I have to be very brief. So, in brief, Bill introduced the all-encompassing geometrization conjecture. His work on geometrization completely revolutionized hyperbolic geometry, three-manifold topology, low-dimensional topology. In the course of his work on geometrization, he generated an incredible number of original ideas. And through that, he created many different new subfields of mathematics. And he revolutionized or re-energized many other subfields of mathematics, all of these subfields distinct from geometrization. Bill also has contributed to many other parts of mathematics. He's been tremendously influential outside of geometrization. In particular, he's done extraordinary work in foliations, rational maps, context structures. Anyway, it's my pleasure to welcome Bill Thurston.
Thank you, thank you. This is just a hyperbolic polyhedron. We're going to switch. There's my. You can hear me now, can't we? Okay. I'm not used to using Keynote, but I'm going to try to use it. Play slideshow. Okay. So I think a lot of mathematics is really about how you understand things in your head. I mean, it's people that do mathematics. We're not just sort of general purpose machines. We're people, and we see things, we feel things, we think of things. So I think a lot of what I did, a lot of what I have done in my mathematical career has had to do with finding new ways to, well, build models, to see things, do computations, anyway, to get really a feel for stuff. And, you know, it may seem unimportant, but, you know, when I started out, people drew pictures of three manifolds one way, and I started drawing them a different way. People drew pictures of surfaces one way, I started drawing them a different way. There's something significant about how the representation in your head profoundly changes how you think. Now, it's very hard to do a brain dump. It's very hard to do that. But I'm still going to try to do something to give a feel for three manifolds. You know, words are one thing. We can talk about geometric structures. There are many precise mathematical words that can be used, but they don't automatically convey a feeling for it. I probably can't convey a feeling for it either, but I want to try. That's what I want to try. Okay, so we now have we have a very strong, clear, beautiful picture for three manifolds. There's every three manifold has a decomposition into canonical geometric pieces. This is very, well, we've sort of known this had to be true for many years. At least I felt it had to be true. And other people gradually started believing in it, not everybody. And Parallelogram proof really seals it, so it's sort of established for the mathematical world. It gives us a place to, it's both, as many people have said, it's both a stopping place, it's the end of an era, but it's also the beginning of something. It gives us a platform for going ahead. We don't have to now hedge everything we say in terms of, well, if the geometrization conjecture is true, then or every, I mean, you know how it goes, that when there's something not quite established, the Riemann hypothesis or whatever, people believe it's probably true, but it's not established, then everything is hypothetical. Everything is, people talk about different kinds of things. Once something is rigorously established, then people go on to do more things. What are we going to go on to do? It's very hard to predict. That's one thing I've learned in mathematics. I thought I would know what was coming next, and it would be completely in a different direction. But still, it's good to try to understand a little bit of what it is. I want to start, though, by just going over one little, so this geometric decomposition is very clear, it's very straightforward in a sense, but it's more complicated than people easily absorb in a casual encounter. And, well, it's very easy to hear about it without understanding it. So I want to go over one microcosm, one world, one little mathematical world that contains all the phenomena in the geometrization conjecture, all 8 geometries and both decompositions, and it's a world that you can actually see and get a direct intuition for without some complicated indirect calculation. It's very important that you see it. If you plug numbers into a computer and do a computation and it says something, it gives you a very different understanding. It's not the same answer as if you see something. So we begin by just thinking of a sort of a magical circle, a loop that doubles the world. So we have a loop here, and when you pass through the world, suddenly you're in the United States, and the coffee is brown-colored water. You go through the loop again, and we're back in Paris, and the coffee means something. And if you want to go back, you can go back, and we're back in the U.S. And okay. Anyway, so the world branches like this. If you went to Gis's lecture, what's the right word? He did this to Poincaré repeatedly. He created a doubled world where Poincaré, we branched copies of Poincaré in more and more complicated ways. I'm going to do much the same thing, but in 3 dimensions. I didn't have the time and energy to put in a 3-dimensional Poincaré here to show you, but you can imagine someone for yourself. Or maybe that joke got worn out last night. I don't know. Okay. But you think of the basic universe as the 3-sphere. The 3-sphere we think of as all of space, but we make it small by doing the 1-point compactification, but a single point at infinity. So, you start out going in any direction, you go far enough, and you reach the point at infinity. If you continue in a straight line, you come back the other direction. I don't mean the projective completion. That's different. I'm talking about the spherical completion, the 1-point compactification. Okay, so we can now do this with other designs, not just a round circle. Oh, if you double the sphere, the 3-sphere around a round circle, you get the 3-sphere again. You can think of just as we saw in Jesus' talk, we can just think of a symmetry of the sphere. If this is a great circle, you can rotate the 3-sphere around the great circle, and if you rotate by an angle of pi, and rotate by an angle of pi again, you come back. So the rotation by angle of pi is an element of order 2, and the quotient by that symmetry gives the 3-sphere, and conversely, the square root process, the inverse branch function. Branching around the axis gives the three-sphere. But we can try it with other more complicated figures. Here are the Boermann rings. This is a famous link. And there are two ways to think of it. Either think of creating this branch cover, or just think of these links as creating a singularity in the geometry of space where a cross-section of the link is like a cone. It's like a standard, well, it's like a cone you get by taking a sheet of paper and take a sheet of paper and bend it two halves together to make a cone. A cone with a total 180-degree cone angle. So we can think of just geometrically distorting space like that. If you do that, the metric will look kind of ugly. But space the three-sphere has a beautiful metric, which is distorted by that cone angle along these axes. If you've seen the movie Not, it tried to give a feel for that. Just as a stepping stone to trying to get a feel for how it works, the Boermann rings can be rearranged in either of these two forms. You can think of, well, you can take three ellipses with their long axes and short axes, all different. And this arrangement of ellipses can be changed into the arrangement of three circles. Now, on this arrangement of ellipses, I've drawn in some two-dimensional ellipses. You can think of that as giving a spine for the three-sphere, with those axes. In other words, everything outside those things, all of space outside those axes can collapse into it can collapse down and fill all the crevices. So it's the outside of these. So if you drew a ball in the three-sphere, it could sort of turn inside out. Anyway, you can think of it taking a sphere and just collapsing it down to here. If you now think of the opposite process, inflate, think of a paper construction made of two faces for each of the ellipses, and they're joined just the way you see them. The visible faces are joined. I don't have it as a live model here, so I'll just talk about it. If you inflate it, can you see a cube? This will inflate into a cube. Particularly if you think of making those axes, as I said, with a 180-degree cone angle. So it's like each of the axes is like taking half of space and folding it in half. So when you inflate it, it just opens out and makes it flat, and it will become a cube. Here's a picture of a cube. It's a little not centered, but I'll go back and forth a little bit. I should have put these on the same page, but so just imagine a paper model with a little hole where you can puff some air. Oops. And it turns it into this cube. And now with the cube, this is part of a repeating crystallographic arrangement in three space. So if you take three space with three sets of parallel axes, a set of axes evenly spaced like this, then an interleaving set of parallel axes like this, so they don't intersect, and then that creates holes where you can make another set of axes going down as it's drawn. If you take a cube, as big a cube as you can that doesn't cross those axes, it will intersect the axes just as in the picture. So there's a group of symmetries involved in space. If you start with these axes, you can think of the symmetry, which is 180-degree rotation about any axis, or or you're here and you go like that, or, well, you have imaginations. I would do it if I thought you didn't. Yeah, you can. So there's three kinds of symmetries. You can do the symmetries about any action, any axis. If you start composing those, you get more symmetries. But this will act transitively on the spaces between the axes. Each cube can be sent to another cube, any other cube, in a unique way. So if you take space with this crystallographic group and form the quotient by the action, so you identify all points that are equivalent under the action, you will get the topologically, you'll get the three-sphere with the Boermann rings as the image of the singular locus. And if you had, if you had some crystallized molecule with this crystallographic group, you could draw a diagram if you wanted in here with, the fundamental atoms would be aligned either on the axes or in between them, and you could figure out the structure from this quotient picture, just as you could figure out the repeating structure here. Okay, so that's one example of a geometric structure in this microcosm world. This is a little special case of the geometrization conjecture. I'm calling them orbifolds/2. They have only cone axes with order 2 cone axes. I'm only just using the underlying space as the three-sphere, and this is what we get. This is the kind of thing we get. Okay. Here's another example of a geometric structure, a little bit more complicated than Euclidean space. This is a picture. Actually, I was reading Poincaré's works. I was reading what he wrote about topology, and he described this picture, and he didn't draw the picture, but this is the picture that he evoked. And I was kind of amazed when I read it. So this is called nil geometry, or we call it nil geometry. So here you can think of space with an affine group of symmetries. So you can, with this picture, this nil geometry, or Heisenberg jungle gym. So you can go up. If you go up one unit, it's exactly the same. If you go over a unit, everything's tilted, but it's tilted in a very predictable way. So when you go from here, you just shear downwards. And similarly, when you go over, I'm going over this way, I shear upwards. So there's a group of transformations going right and left, forward and back, and up and down. They're not preserving the Euclidean geometry, but they're preserving some other kind of geometry, this Heisenberg geometry or nil geometry. This is another one of the 8 three-dimensional geometries. It doesn't actually occur very often, but it occurs, and it's important in understanding the whole picture. It's important to understand the special cases as well as the main cases. So this is one of the special cases, nil geometry. And the quotient, well, I wasn't totally careful to draw the picture that corresponds to this picture, but here's an example of a link in the three-sphere where if you think of this link divided by 2 with order 2 cone axes, it has a nil geometry structure. And, rather than all these things, they're possible to carry out in detail, but in a way, the bigger point is to try to be able to squint your eyes and sort of kind of get the feel for it. I mean, you won't get the exact feel for it just if you haven't seen it before, just on one glance. But I'm going to go back and forth. These axes here these all four circles correspond to, all four circles correspond to the vertical lines. All that's drawn are the vertical lines. And there's a weird thing. If you look at these vertical lines, the figure has, it has order 2, you can do an order 2 rotation about any of the vertical lines. But now, if I take the 4 posts surrounding a square, and I rotate 180 degrees about one, and 100, I progress around the thing. If I was doing that in Euclidean space, doing those 4 rotations would get me back exactly how I started. It would be the identity. But when I do this, I sort of drift upward. So the group generated by 4 rotations around 4 adjacent posts has a compact quotient. And the 4 posts, in other words, there's a kind of warping here. The posts are warped with respect to each other. And you can see that here. I mean, I could have drawn this picture that emphasizing that. It would have been better rather than a flat picture to draw a sort of vertical picture where these 4 posts sort of go around and sort of twist before they come back. It's the same thing. But they're like 4 posts with a warped relation. But in fact, these are 4 Hopf circles. They're part of the famous Hopf vibration of the 3-sphere over the 2-sphere. And so you can there's actually a rigid motion. There's an isometry of the 3-sphere that sort of rotates these 4 circles along themselves and rotates space around them at the same time. And if you take the quotient of the 3-sphere by that circle group action, by the motion that rotates all those 4 circles simultaneously, the quotient will be, well, it'll be a 2-sphere where the 4 axes become 4 special singular points. So this is the 3 orbifold that fibers over the 2-2-2-2 two-dimensional orbifold. I mean, just to show I'm not even sure I put all the slides in for all the geometries. We can do some of these quickly. Here's a link whose geometry gives us two-dimensional sphere across a line. If you just take 2, in fact, that would work too if I just took 2 disjoint circles, but it's sort of boring. It's like if you have these 2 gates, this one goes from Paris to New York and back again. This one goes from Paris to Moscow or St. Petersburg and back again. But then if you go, if I go around through this one and then come over through this one, you don't know where you'll get. It might be someplace else. So you start considering all the combinations, and you end up having an infinite number of possibilities. And that's like a line direction in this geometry. I just put in this linking sphere to make it look slightly athletic, or to make it, I don't know. Anyway, it's a sphere across a line geometry. Here's a link which gives solved geometry. I think I have a picture of this. Yeah, here's another picture. Again, Poincaré. I learned about this geometry from Poincaré once again. So you can consider space with, we have a group of translations going this way, a group of translations going this way. And now we have a strange thing that you go from this level up to the higher level, and the grid of city blocks gets distorted, so they're longer this way and shorter this way. Anyway, I think this is the 2-1-1-1 map. Oh no, it's the Fibonacci map. But 0-1-1-1. Anyway, as you go upward, everything gets very elongated in this direction, as you go downward, everything gets very elongated in the perpendicular direction. I like to think of this as a system for constructing freeways. I mean, not that I advocate it, but it's a description of a system for freeways where if you want to go a very long distance, you go up till the roads are going super fast in one of the coordinates you want to traverse. Then you go along those roads. Then you come down, and if you go down below where you started, and the roads go super fast in the other direction, and you come up. And anyway, in this horizontal plane, you can within this graph, within this picture, the distances in the horizontal plane are proportional to the log of the Euclidean distance. And in fact, this particular design is, really for that reason, this particular design is very close to designs that are used for switching networks in telephone systems and networks of parallel computers and so forth. They all seem to be closely related to this particular kind of geometry. So this solved geometry has a certain, solve is somehow an appropriate word. I mean, it originally meant it had to be it was a solvable Lie group, which is simpler than other kinds of groups, but it's also good at solving problems, and that there's a theorem that if I take an arbitrary graph of finite valence, I can quasi-isometrically embed it, quasi-uniformly embed it in this with only a sort of a logarithmic expansion, expanded by the log of the number of nodes. Anyway, and here's an example of a link which, when you unwrap it, when you unbranch the space around this, you branch space around this link, it gives solved geometry, where you can think of the curve here is on one horizontal level, the curve up there is on another horizontal level, and the weaving back and forth stands for the vertical lines, and there's kind of you can kind of see if you take the loop at the bottom and push it up to the top, it gets twisted around as measured by the top. And one can actually continue doing that, and it gets more and more twisted. That's very like the solved geometry. It's very like this picture here. Now, again, I don't expect you to get this in detail, but I'm just trying to say there's an intuitive relationship. You can learn to look at this, and you see it's like this. I mean, there's a lot of techniques to help do that, but here's just a random example of another one of the 8 geometries. This is like the others I've talked about so far. This is based on two-dimensional hyperbolic geometry, sort of extended. It's based on a two-dimensional picture, but extended one dimension higher. It has to do with, you can think of it as describing the set of positions of a ship sailing on a hyperbolic sea. So it's the unit tangent bundle of the hyperbolic plane. This is kind of geometry. And these are just 5 hop circles, 5 circles of the hop vibration. If there's a kind of, again, there's a motion, a continuous motion of the 3-sphere where I can think of just continuously rotating all the circles all at the same time, and it extends to the space around it. They all sit on the surface of a torus, the way they're drawn. You can think of rotating the torus this way and rotating the torus this way at the same time. And the circles go to themselves. And the orbit space of that action, the quotient space, is topologically a 2-sphere with 5 circles. It'll actually look like 2 copies of a pentagon in some sense. So in the hyperbolic plane, you can there are right-angled pentagons you can make. If you take 2 right-angled pentagons and sew their edges together, it makes you can think of like a pillowcase, a pentagonal pillowcase. And this is just And you can think of the circles as just describing, of course, this pentagonal pillowcase is a two-dimensional surface. But if you think of the set of all directions, so your kid takes a pen and marks on it all possible ways. It makes little marks. This is not just theoretical. Anyway, the possible ways to mark, there's a three-dimensional set of tangent vectors to this pillowcase. And this is related to its picture. It's not exactly the picture. It's good enough right now. It's a very similar thing. This geometry is related to the hyperbolic plane cross a line. Okay, this knot is one of the very simplest ones where the orbifold, you divide it by 2, or take the twofold universal Franz cover, and it's hyperbolic. I won't say it's the simplest, because that would depend how you define simplest, but it's one of the simplest. And really, it's the generic behavior. All these other things I've talked about so far are very, very special cases. If you take a sort of generic thing, a typical, very tangled knot, it tends to have a hyperbolic description, or depending what you define as a random knot, it might tend to have some small little pieces that have other kinds of geometry, but the bulk of it, the big component, would be hyperbolic. Now, can I show you why it's hyperbolic? So the complement of this has an amazing kind of geometry. I felt inspired to try to build a spine for it by hand. I don't think you can really appreciate it from these photographs, but that's what it is. You should think of taking these are 5. They're triangles plus half of a tengon, and there's one more tengon you should really put in the middle, but it doesn't show. Anyway, here's the fundamental domain, the Dirichlet domain for this group acting in hyperbolic 3 space. If I'd been more organized or had more time, I would have shown it more. Let's see, this is GeomView, which a lot of this software used to work better than it does now. No, I want the cameras. I want to go back into the, the window's smaller than I was. Yeah, I can change it back to the conformal model. Here, I mean, this is what it looks like. This is what the fundamental domain for that universal, for that Turk's head knot looks like inside hyperbolic space when you unwrap it. So it's made of, it's actually a regular hyperbolic. There's a form which is a regular hyperbolic polyhedron. I'm not sure it's still regular here, because some of these operations might have distorted it a little bit. There are many choices for the fundamental polyhedron, but it's made of, it's a truncated dodecahedron. You start with a regular 12-sided figure, and then cut off the faces cut off neighborhoods of vertices by triangles. So the faces are tangons in triangles. To glue it up, to give the Turk's head knot, you actually take there are two of the tengon faces, like this red one here and this other red one here, which just join together. If you can think of taking the figure topologically and joining those two together, it'll make a solid torus. And the solid torus, you got, oops, I have to go back to where is it? Keynote. I have to go back to here. The solid torus you got is the complement of this figure I've drawn. And then all the other faces, if you can actually fold them up in space, and it'll create this spine where the cone axes go to the red axes of the spine. Anyway, it's just one example. This is one example of how a knot or a link gives the surprise. I mean, there's a sort of canonical geometry associated with it. There's no choices about the geometry of the orbifold or manifold you get. And it's often very surprising and striking. This is a slide I meant to have later. So we'll come back to it. Now, I've talked about most of the geometries. I'm not sure I mentioned all of them. It's not important because most of them are minor geometries. I just wanted to give a flavor. The main geometry is hyperbolic geometry. But there's also two decomposition theorems to really understand three manifolds and this microcosm of these /2 orbifolds. So one is the prime decomposition. This is something well known in knots. I mean, when you learn to tie a square knot, you tie an overhand knot, and then you tie another overhand knot. The square knot is the sum of the overhand knot plus the overhand knot. To recognize when something is not prime, the question is whether there's a two-sphere that intersects the knot or link in no points or 2 points. If it's connected, you can't have it. I mean, if it intersects in no points, then it's a trivial two-sphere. It doesn't matter. If the link, yeah. Anyway, so here's an example where there's a two-sphere indicated by the red line where it intersects in 2 points. In the prime decomposition, when you find one of those, you then join the loose ends and you get two simpler knots. And the nice theorem is that even though you might find different ways to cut it, but when you get pieces that can't be cut anymore, the set of pieces of a knot you get are canonically determined by the original knot. The prime sum ends are uniquely determined. And I won't go through that theory. Okay. Now, there's another decomposition which John Conway pioneered, the tangle decomposition of a knot. So to understand the tangle decomposition, you look for two spheres that intersect the knot or link in 4 points, like I've shown here. And the theory is somewhat more complicated, also somewhat simpler. So to do the tangle decomposition, if you find a sphere that intersects in 4 points, you get 4 loose ends. There are lots of possible ways to join up 4 loose ends. You could join them like this, you could join them like this, or you could do a big twist and join them like this, or you could twist this way, twist this way, twist this way. There are infinitely many ways to join them up. So what do? You give up. I mean, you just put them all in a point. You gather them all to a point. And you sort of almost inevitably led to this new concept where now instead of having just a knot or a link, we'll also have vertices where 4 strands come together. And we think of the vertex as just a locus that's ready to implant another tangle. So you might put a little overhand knot, or there's, again, a nice collection of ways. The set of possible ways to do it are described by elements of the rational projective line, or actually, a pair of relatively prime integers up to sign is the way to say it. And again, there's a canonical aspect to this. If you might find more than one different way to cut a knot into tangles, but the answers you get are the same if you define it correctly. Okay. Okay, so that's the theory. This is a very, very powerful theory, this tangle theory. I'll come back to it in a minute. There's sort of a... So one of the directions, I think, it's just begging to be developed better is the issue of computation of three manifolds. So we have some computational tools for three manifolds that are just remarkably effective if you understand the tools and how to use them. They work very quickly. I'll show you in a minute one of them. On the other hand, there are many ways to ask questions about three manifolds that are sort of fit into the, well, they're known to be NP-complete, or they're known to be, very hard to answer. And so it depends somewhat what questions you're asking, how easy it is to compute. But the most important questions might be, we have some topological description of a three manifold. Can we canonically identify it? Given two three manifolds, are they homeomorphic? And it's not known, but it appears to be that they're probably quite efficient algorithms that work. But, in practice, they're very efficient algorithms that work. But why? And how do they work? And do they always work? Those are questions that have never adequately been addressed. It's easy to prove there are algorithms that do work, but the only proofs I know about involve these sort of doubly exponential things, or they quote the solvability of, it's known that the elementary theory of real numbers is solvable by, Tarski proved this amazing theorem, but the algorithms are very bad. But for three manifolds, the algorithms seem to be very good. So, I think the central focus of this is emanated from Snapp, which is a program Jeff Weeks began as a PhD student. He was sort of kind of thinking of dropping out because he didn't think he was set to be a research mathematician, but he went off to teach at a college, a teaching college for a year. But but I thought Snapp was worthwhile as a central point of a thesis. So anyway, he wrote a thesis surrounding that, and then he's developed it a lot ever since. And then a lot of other people, too, have helped and written other programs, and et cetera, et cetera. But a lot of it comes back to Snapp. Let's see if I have yeah. So unfortunately, oh, shoot, this is distorted here. I'm going to try something. I'm going to quit this. And I'm going to restart it and see if it gets a better perspective, because this is a run. Okay. This is an emulator of a very old-fashioned Macintosh. I see it's distorted in this. It doesn't understand the display, so we'll just deal with it. So this is an example of a program that it was faster 20 years ago than it is now. But someday, there are other modern versions that are quite fast, but they don't have the same nice user interface. So let me see if I can do this. I wasn't expecting, no, come on. Do we have new link projection? Okay, we'll try this anyway under duress. I could go to a modern version of Snapp, but so basically, I can draw a knot or a link. I'll just draw something. I'll just put in a few circles. Come on, close it up. I'll draw another one. I want it to be not too complicated because the program is inefficient running in this this Motorola, this emulator for an old chip. It's not even the, anyway. I'm going to make it alternate. Now I can, so here's an example of a link, not terribly complicated, but not terribly simple. Now I'll ask it to find a hyperbolic structure. It did. Its volume is 29.1585958228284, as you can read. It's possible, of course, to compute this as accurately as you like. So that's a unique topological invariant of the knot, but volume of a link complement does not uniquely characterize the link. Given a certain volume, given a certain value for volume, there's only a finite number of possible different links with that volume, but we don't know what they are. We don't know what the values of volume are, and we don't know what the set of volumes are. I think tomorrow we'll hear from Dave Gabay about that we now know what the lowest volume for hyperbolic figure-outable is, but in general, it's a very difficult question. However, there is combinatorial information to do it. What I wanted to show, this is a different metaphor. This is a different world now. In the notation where I was talking about knots divided by 2 before, here this is a knot divided by infinity. So it's computed a hyperbolic structure where you can think of making it the knot into an order 3 cone axis, an order 4 cone axis, order 1,000,000 cone axis, and there's a limit as a million goes to infinity, where the knot itself is infinitely far away. So there's a metric in space. There's a metric on the 3-sphere, which is hyperbolic. It's a metric on the complement of the knot, everything but the knot. The knot is a singularity, it's infinitely far away, but the neighborhoods of it get really, really thin. They sort of decrease. They're like toruses going around the knot shrink exponentially fast as you go toward the knot in the metric. So this metric has a finite volume. It's a complete metric of finite volume with very standard cusps. One invariant for the knot is the shape of the cusps. Unfortunately, these are going to be distorted by an affine transformation, but there they are. You can't see it very well, but these toruses are just all similar toruses, but they shrink. So the shape is well defined, just the size is not. And these are the shapes. They're kind of long and skinny. That's typical for alternating knots like this is. There's a lot of theory about what the shape can be. And that's, again, a topological invariant of the link complement. I'm going to see if I can... I'm going to see if this emulator is good enough to compute the cusp neighborhoods. This used to be, quick. Or on a modern, there it is, okay. It's going to do it. I'm going to, I'll show you another view that gives you an idea of why there's a canonical combinatorial picture. You have to imagine, these may look like circles here, but they're real. They may look like ellipses, but they're actually circles. From my point of view, they look like circles, actually. So this picture is a canonical function of the topology of that link complement. There's some combinatorial information. No, sorry. There's some combinatorial information that goes with it, namely the Ford domain. here it shows it. And I'll show the parallelogram too. So you can think of, I have to shrink it so we can see it all in one picture. Okay, you can see I don't know if you can make it out, but there's a parallelogram in the picture. The parallelogram is meant to be identified to a torus. And this torus stands for a torus going around the blue link component in the original picture. There it is. So if you make it, redisplay is painful. Anyway, if you make a little torus going around the blue link component and a little torus going around the red link component, and you think of inflating them, blow air into this one, blow air into this one until they touch, they will touch on, I'm sorry. They will touch on those parallelograms. I'm going to take away the horizontal just so you can see it. There's a combinatorial pattern where they touch. I haven't shown the red one, but they touch in the same way. So again, this combinatorial gluing pattern is a canonical function. It's a canonical combinatorial function of the knot. Any other, if you distorted this knot, drew it any other way, or embedded it in space in any other way, Snapp P would find exactly the same picture, and you can recognize and totally identify the manifold by that pattern. And this is quite general. Okay, so I said some of this already. The way these algorithms actually work is by starting with the knot, finding a combinatorial decomposition into what we call ideal tetrahedra. They're like tetrahedra with all their vertices missing. Their vertices are kind of spiraling toward the knot. And then it turns out the shape of an ideal tetrahedron is very simple to describe. You can determine it by a single complex number associated with any particular edge. It's like an angle. It's very much like an angle, a generalization of the angle of a triangle. And there's an easy formula to get from one pair of opposite edges to the other three pairs of opposite edges. And then there's simple gluing equations that the product of these numbers going around any edge has to equal 1 because it has to match up. And then Snapp P and similar programs work just by numerically solving for when the gluing equations are true. And what seems miraculous is that they almost always converge. I mean, why should they? These are equations with, as soon as they get a complicated knot, each crossing kind of multiplies the degree of if you wrote it as a single polynomial equation, it multiplies the degree by 2 or something like that. So do 100 crossings, it would be degree 2 to the 100th. It's an algebraic equation. It's certainly algorithmically solvable. We're looking for one particular solution, but we zip right to it with these programs. How many? Just a few minutes. Okay. Yeah. Okay. So let me give the rest of my talk. So they're good serial numbers. I think there has to be something more going on, and somebody needs to figure out what it is. So in practice, we have really good ways to identify three manifolds. There are a lot of other mysteries remaining, so I just want to touch on them quickly. And I should have my time here, but I don't actually have a watch. So one of them is there are many structures associated with three manifolds. One of them is the fields, the algebraic and the information in the number theory. So any hyperbolic three manifold is associated with an algebraic number field, canonically associated with that field. And there's more algebraic data as well, but let's just start with the field. And there's just a basic question about what fields arise in this way. There's an easy statement that the field has to have at least one complex place. So and anything that has exactly one complex place occurs as an arithmetic three-manifold. But there are lots of others that are not like that. And I kind of suspect that it may be that there's a hyperbolic three-manifold associated with every number field that's not totally real. But it could be right or wrong, but it's a very fascinating and mysterious question. I wish I knew how much time I actually had. I have to look at my iPhone. What? A minute, okay. Okay. Another interesting structure is to try to understand another thing I think we'll be trying to understand for a long time is how to understand the set of all three manifolds. So just because we know how to identify a single one, we have one credit card that's valid, it doesn't mean we know what are all possible valid credit card numbers. We take a random number, you can check if it's valid, but it doesn't mean you can just give a random number to the hotel and have it work. So, not that I try, but but there are some very nice structures that encompass all three manifolds. One of these is the Dane filling space. And it's a kind of metric complex where you can measure, it has these sheets where you can measure the distance from one to another along a sheet. Given two manifolds, we can try to navigate within this space to get from one to another. If you generalize it in the right way, it's actually not dissimilar from the kind of space of metrics as Boermann might have looked at. I mean, there's some things that seem similar, analogous to the Ricci flow, but haven't been made to work using these combinatorial geometry. Skip that. Skip this too. Well, let's give people some breathing room. Stop. Okay, so there's time for -2 questions. Anyway.